All right, good morning. So we're going to continue discussing advanced finite volume. So the first thing we want to do is to close the loose ends we have on the last lecture on total variation diminishing. Last lecture, we coded up a second order scheme for solving the Burger's equation with finite volume. And we tried to impose a flux limiter on the solution so that basically the extrapolation wouldn't create new maximums or minimums. So what we did is instead of treating the finite volume solution as piecewise constant, what we did is we used the finite difference to reconstruct the gradient in each volume and use the gradient information to extrapolate to the interfaces. In particular, if we have an interface xi plus half, we reconstructed the gradient on the left-hand side cell and another gradient on the right-hand side cell so that on the interface value, we have a left value and right value. So left at interface, this is right at interface. And we use the left and right value at the interface to fit into the Goodenough scheme for computing the actual flux on that interface. And that flux goes into the time derivative of the volume averages, which drives the finite volume scheme. So last lecture, we imposed the flux limiter so that we don't create new maximums or minimums, but we still see oscillations around shockwaves. So I went back to look into why that is the case, and let's actually try to repeat what I did in class, so that kind of illustrate what's the process of debugging a numerical phenomenon. Okay, so this is the, let's see, so this is the DDT finite volume. This is the same code we left at the end of the last lecture, and the phenomenon we try to create is if we have X being a periodic solution, let's say from 0 to 2 pi, and the initial condition is a sinusoidal wave. So what we did is in the last lecture, we used the OD45 to integrate this DDT finite volume for a period of, I think, pi. And I use U0 as initial condition, and we plotted the final solution, and we still see oscillations even with the flux limiter on. So why is that the case? Well, let's figure out why it is the case by trying to catch what it is not supposed to do. What total variation diminishing scheme is not supposed to do is to increase the cell average that is already a local maximum, or decrease a cell average which is already a local minimum, right? So let's put a breakpoint over here to see when it is actually the case. So what I'm going to do is I'm going to identify the cells over which it is already a local maximum, which is saying my solution W is greater than the previous cell solution, which is this, right? So if my W is greater than the cell on the left, I'm going to put it as one of the conditions, and another condition is W is also greater than the cell on the right, which is this array over here. So this is AND, right? So this is basically an operation across the entire solution that is going to give me a Boolean array of 0 and 1s, truths and falses. Okay, and I'm going to put another AND over here and saying that the solution is still increasing, which means dW dt. Let me say, put it over here. And dW dt is greater than 0. So this is supposed to be all false, right? If I have a total variation diminishing scheme, the goal of the total variation diminishing is to prevent such situations from happening, is to enforce that a local maximum can only decrease, or at least not increase, and the local minimum is supposed to not decrease further, right? Okay, so let me say that is impossible is equal to that. Okay, so then I'm going to put a breakpoint over here saying that if sum of impossible is greater than 0, I'm going to break. So I'm going to print impossible and put a breakpoint over here. So here, now let me call this again, call the OD45 again, and here I catch a situation that's not supposed to happen, right? Okay, so let's actually look over here to see what the solution is like. So here we are inside the execution of this function, and I can plot what W is. So W, it's still like a sinusoidal wave. And where is that impossible happening? Let's go find impossible 26. Okay, so basically around here, let's put a grid. And so basically we see that what's happening is this particular local maximum is actually supposed to increase further. And why is that the case? Well, notice that the dw dt, I mean, the first two conditions are obvious because we always would have a local maximum around here, right? The key question is, why is dw dt still greater than 0 here? It is greater than 0 just from the finite volume formula. The time derivative is equal to the flux coming in from the left minus the flux going out from the right, divided by the size of the volume. So the time derivative greater than 0 basically says that the flux from the left is actually greater than the flux at the right. So let's actually look at what it is. FL at 26 is 0.5005, and FR is actually a little bit lower, right? So that's the reason why the cell average is still increasing over here. Okay, so now the next question is, why is the flux on the left higher than the flux on the right? So in order to answer that question, we need to know, let's say this is the problematic cell, for example. We need to figure out what is the left and right reconstructed value on the interface on the left, and what is the reconstructed value, let's say, on the right interface, right? So that is again in the code. So basically we trace back from where the problem occurred to why it occurs, basically backwards through the calculations. Now we come to the good enough flux calculation. So we know the good enough flux, the problematic areas are, let's see. So the good enough flux is it fits into both FR and FL, right? So basically FR at cell 26 and 25, which is actually FL at cell 26, is the source of the problem. So basically we actually would want to look at FR 25 to 26, right? So the first number, which is the flux on the left, being higher than the number on the right, is the source of the problem. And the inputs to the flux computation is WPL and WPR. So let's say WPL, which is on the left of the interface, is this, and the WPR on the right of the interface is this. So the first thing we notice is that both the left and right values of the cell is actually the same, right? So on interface 25, so basically WPL and WPR are indexed by the interface, right? So on 25, both left and right values are consistent, slightly higher than 1, and on the right value is also consistent, slightly lower than 1. Okay, and so here we see that why the flux on the left is higher than the flux on the right. It's simply because the value of the solution on the left is higher than the value of the solution on the right. And the flux for Burger's equation is the square of the solution divided by 2. So the left actually should be higher than on the right. And I have not created any new maximum because my W at 26 is actually 1.005. I mean, the flux limiter is doing its job in preventing the reconstructed values, which is this value, to be any higher than the solution that is already a local maximum.